How are you?
Okay, let's get started on time. My name is Venkat Guruswamy, and I'm a senior scientist and interim director here at the Simons Institute. And it gives me great pleasure to welcome you all to the Simons Institute and this week's workshop. Just a brief introduction about the Institute. It was founded in 2012 with a very generous grant from the Simons Foundation. And it's arguably the world's leading collaborative center for collaborative research in theoretical computer science and related topics. And every semester, it hosts thematic semester programs on important topics in theory and related areas, which bring together a large group of researchers, junior and senior, as well as some postdoctoral fellows associated with the program to spend time and push the frontiers of the subject. And one of the things about the Simons Institute is that it really has a very outward-looking view of what theory could and should be, and its impact in broader science, engineering, and society. And a testament to that is this year, where we have a special year on large language models and transformers, which actually spans both the semesters. And we are now in part one of that program. And in particular, this week is one of the workshops associated with the LLM program on alignment, trust, watermarking, and copyright issues in LLMs. And I would like to thank the organizers for putting together a really exciting program with a couple of panels, really talks on a whole gamut of issues spanning these things. And the organizers are my colleagues Shafi Goldwasser and Raluca Popa, as well as Dylan Hadfield-Meneley and Ankur Moitra, both from MIT. And just a few logistics for the coming week before I hand it over to Shafi to introduce the workshop. We have food before the first talk and during the breaks, just outside the auditorium. For lunch, you're on your own, but there are many choices in short walking distance, and you can leave your belongings in the lockers on the other side of this corridor when you go out for lunch. And we ask that you please refrain from bringing any food or drinks. Water in bottles is okay, but no coffee, no food, please, because it helps us keep the auditorium very clean. And our videographer, Omiyad, will be around throughout to help you with any AV issues. And also, if any of you are active on X or other social media, please consider live tweeting about this workshop, especially this particular workshop on the topic be of interest to a lot of people. And tag us at Simons Institute, and we'll make sure to retweet your post so that this science can reach even wider audience. And of course, as always, all our talks are recorded and live streamed, and enjoy a healthy life on YouTube later on. And special thanks to our event staff who work tirelessly to put events like this together. For us all, it's maybe one event occasional week. They do this on a routine basis and do a great job handling all the food and other things, as well as arrangements for out-of-town visitors. So a huge thanks to all of them. And with that, I'll hand things over to Shafi to introduce the workshop.
And thank you, Venkat, especially for being a great director and also much more eloquent speech giver than I am at all with his introduction. Anyway, thanks everyone, and welcome to this workshop on alignment, trust, watermarking, and copyright issues. So the truth is that the title is actually is much narrower than what we're going to present in this workshop. And I think these are extremely important topics that not only they're important, but the theory can actually make a difference. I'm not sure we can have the compute power that the industry does, but we certainly have brain power. Not that they don't, but we have some left. In any case, so there is something that academia and theory can really contribute, I think, on these topics. And we try to organize it thematically in terms of the days. Today is going to be a lot of issues of security. There's going to be a panel from 4 to 5 on regulation, and people are sort of for and against. I think it'll be an interesting panel. Then tomorrow, most of the day is about using sort of proofs in one way or another in the context of LLM. The third day is on issues that are more related to alignment, and the fourth day is issues like watermarking and copyright. And we will end actually in a workshop in the fourth day, which is sort of a brainchild of the last minute, which is called are LLMs or is AI going to make us personally stupid, and what can we do about it? And I think we've invited some people who are kind of outliers, not really typical people in this field, some from law, some from other disciplines. I think will be quite interesting. So Now I'm introducing Raluca, who's my co-organizer, and it was a wonderful co-organizer. She's very responsible, and she's gotten all the speakers. And thank you, Raluca, and she's going to give the first talk. Thank you.
Thank you, Shafi. Can you guys hear me? All right. Well, thank you so much for coming at the very first session. I'm just really happy to see so many familiar faces, some that I haven't seen in a long time, or I don't know, maybe. Thank you, thank you. I wasn't sure if I was dreaming or not, because these days with a newborn baby, I don't know as day or night. So, yeah, exactly. Maybe I'm still sleeping because the newborn at home, I don't know when is day or night. Okay. So I'm going to tell you about private retrieval-augmented generation and our system Compass. And this is a very recent work, fresh off the press. We have just put it on ePrint archive if you want to read more beyond the talk. And this is joint work with my wonderful student, Jinhao Zhu, who's here, and as well as with Liana Patel from Stanford and my colleague, Matej Zaharia. And Jinhao gets a lot of credit for being the lead author on this work. All right, so retrieval-augmented generation, or RAG in short, is a very basic component of the LLM pipeline. And that's because it basically brings a knowledge database to the LLM, more knowledge beyond what the LLM can actually capture within its weights. For example, without RAG, the user asks a question like, who won the Nobel Prize in Chemistry this year? And the LLM might say, oh, I don't really have up-to-date data, okay? But if you have a knowledge database of, let's say, the web pages that are crawled and whatnot, then LLM can actually use that information. So in a RAG system, the user is first sending the query to a retriever. This is the retriever in RAG. And the retriever is going to send the RAG query to a knowledge database. So this knowledge database contains embeddings, large vectors that capture the meaning of, large number of documents, photos, or whatnot. And is going to perform, the database is going to perform a nearest neighbor search to find the documents that are most related to the RAG query. And then it's going to return this related knowledge, and the retriever then can send this query with the related knowledge to the LLM, who can provide a much better answer. Okay. The challenge that this work is addressing is that the knowledge database can be sensitive. Okay, so it can have private user data. For example, a lot of companies are using RAG on their user data, like user medical data or user financial data. Or, for example, if you're a personal user wanting to use RAG in your iCloud applications, again, a lot of these things happen behind the scenes, you don't know it, but then the RAG is going to happen over your iCloud photos and text and whatnot. So it's very, very sensitive, right? And we're concerned about an attacker getting access to this data or insider employees. Okay, so how do we protect this knowledge database, and how do we protect the query that goes to it as well in the results? So I have here an anecdote from Shafi, who was telling me just a few weeks ago how she was using a modern tax preparation software with AI, and she was surprised how much it knew about it and was able to populate personal information about her. Most likely it was using RAG, again, against the personal database. All right, so in this work, our goal is to protect the database as well as the query and the results. Okay, this is what we mean by private RAG, to provide end-to-end encryption essentially for the database and the queries. Now, one thing we're not concerned with is the actual secure inference. Once you get the knowledge, this can be paired with existing protocols for secure inference like Iron, Mariel, Bolt, or alternatives using trusted enclaves that a lot of the major LLM providers are actually implementing. So you could use our work in conjunction with one of those, or you can use it as a standalone for semantic search. For example, if you're a user, and again, this semantic search is going to happen on your iCloud files without you knowing when you search for something. Okay? So basically what Compass provides is encrypted search on an encrypted database of embeddings. The high level, and these are, again, semantic search is what's used today, right? So we no longer use keyword search, we use semantic search. Search on embeddings, search that captures the meaning of the query. All right, so basically our user makes a query to the retriever, and then the retriever sends an encrypted query to the database of embeddings, which we keep encrypted. There's an encrypted results that come back, and the retriever then returns to the user a ranked list of documents based on the relevance of the query. So this is the setting we work in. Is it clear? Is the setting clear? I'll explain more the security guarantees and whatnot. Okay, setting is clear, great. All right. So in terms of security guarantees, first let's talk about the threat model. We actually have a very clean threat model in that the server is fully untrusted. It can be a malicious attacker for the cryptographers in the room. For the non-cryptographers, basically the server can deviate from the protocol arbitrarily. And we don't assume trusted hardware on the server, and we don't assume distributed trust or anything like this. Now, the client is trusted because this is the data of the client. The client is going to make a query on their own data stored at the server. All right, so at the high level, what are the security guarantees? And then I'll explain how the formalism proceeds. The server will not be able to learn the database, the query, and the results. So think of it as encrypted, and the server is doing the work, but it doesn't actually see the query or the database or the results or any intermediate value. More than that, the server cannot tamper with the results. So if it can tamper with them, but then the retriever is going to detect it. And also, there's no access pattern leakage. So for people who are familiar with encrypted search, you know that there's a long literature of search that is a little bit leaked in order to be efficient. And normally what it tends to leak is which parts of the database are accessed, like which addresses. And from that, there's a line of work of attack showing that you can actually infer the query or the database or things like this. So in this work, we actually don't have any access pattern leakage. Basically, intuitively, for the non-cryptographers, you can think of it as accesses to the database look random. Even if you access the same element over and over again, accesses look random. But we don't protect against those attacks, so the server can just deny service, stop executing if it wants to, and we don't protect against timing attacks, like information you can infer from the user, the time when the user sends the query. Any question? Yeah.
The database could be multiple rounds,
Yes.
potentially,
Yes.
right?
Yes.
And should I think about the model as living on the user's end, sort of locally, for simplicity?
The model?
Yeah.
Yeah, so in this case, we're focused on the retrieval part, right? So you send the query to the database. Here you have a search in embedding space. Now, if you talk about the embedding model, then the embedding model that computes the embeddings is going to live in this retriever. So whenever you get a query, the query is going to be converted to an embedding, which is a vector, according to an embedding model. And that embedding model gets trained before, like use an existing one.
So in the big rank setting, right? I mean, I make a query, I get an answer.
In the bigger rank, yes.
Sort of local model, do mail rounds. Maybe.
Yeah. If you want to use this just for search, then this is the whole setting. If you want to use it for as well for the model, with the model as well for the bigger rank setting, then the model would also live here. Would live on the server and you do secure inference.
But I could think of it as living at the retriever's end, right? I mean,
you could. Yeah, you could also do that. It's honestly, it's independent. Like it's completely independent. What we do here is we just do the retrieval on the encrypted database of embeddings. That's the only thing we do. Now, how you use it, you have a variety of ways to use it. You could have the model if you wanted the retriever on the client side, sure, and then you just outsource the database. Or you could also want to outsource the model. There's work on secure inference outsourcing the model. You have a bunch of that work as well in the past. And yeah, now, there's another model, and I thought initially you were asking about that one. There's the embedding model. We don't need to get into that. That converts the query into the embedding. No need to get to that. You can assume the query gets converted into an embedding by the retriever. Yeah, great question. Great clarification.
Quick question. This outsourcing, is it per retriever? Is it like a database that can be shared used by many retrievers? So it's like for each retriever you need to outsource separately?
Very good question. So basically you have this database. Let's take the iCloud example. Because they're actually interested in this kind of scenario. In your iCloud cloud will have your encrypted files, your encrypted database of embeddings, and it's going to have it encrypted for every user, but we instantiate Compass independently for every user. So you can search on your own embedding data, you search, you have your own local search that goes to the cloud and whatnot, and another user is separate. So you can imagine having all these different encrypted databases for each user. And for now,
at least for PIR, there are models where I guess there is like one PIR database and many people kind of access it. But yeah, I guess it complicates secret keys and stuff. But yeah, this is per user.
Yeah, exactly. In the PIR case, where you have a public database that's maintained and owned pretty much by the cloud, by the provider, then it's a different setting. You have many users querying it. Here's a setting where you have personal data. right? So you have your personal iCloud files and photos and whatnot, and you have them stored in the cloud. Yeah.
I mean, your Nobel Prize example wasn't personal data, right? So there's some unencrypted data. So there's also maybe lots of public data.
So the Nobel Prize example was mostly to illustrate kind of the RAG case, but the Shafi example, for example, is a private one, and also the iCloud example is a private one. Now you have a good question, like could you combine our system with public database? You could. You probably would do other techniques, PIR-like techniques for the public database. You wouldn't do our techniques, as we'll see. They're not as developed for that.
In this database, for now, it's static, right? Or you have a simple example?
Oh, you can easily insert. So if the file gets more documents, images or whatnot, it can insert in this. We'll see how it works. There's an index in here and can insert in it. So basically, it's the classical setting of encrypted search. Encrypted search setting. The difference is that it's semantic search. It's search on a database of embeddings, like people modernly do today, and not search on just keyword search. Great questions, great clarifications. Okay, so I'm not going to go in detail over the security definition, but it's a pretty standard security definition for encrypted and oblivious search. It's an indistinguishability-based definition where you have an attacker and a challenger. The attacker is able to choose two databases, and the challenger has a bit B that only the challenger knows. It's chosen randomly, and the challenger is going to encrypt one of these databases. Then the attacker can choose pairs of queries, and they're going to engage in the Compass protocol with the attacker behaving as the server. Okay, the attacker can misbehave, but in the end, really the challenge is to either guess in which world it was or to affect the computation result. Okay, so I'm going into this. It's pretty straightforward definition. Also, our building blocks for achieving security are just standard assumptions. So let's work on how are we going to make this work, okay? And I'm going to get a bit technical, I think that's the idea of this workshop, is to get a little bit technical. So definitely feel free to ask questions if something is confusing. So first, like the very first question is, okay, why can't we use existing work on encrypted search? There's just such a long line of work in that space. As I mentioned, it's focused on keyword search, like exact match of words, which is also called in the machine learning literature as lexical search. And I have here a few categories of major works in the space. One of them is the leaky search, starting from the seminal work of Song, Don was here, Perig, and Wagner. And basically, this one is very efficient, but it was leaking these access patterns that I mentioned. It can extract a lot of information. It's also keyword search. Keyword search is not as accurate. Then we have work based on trusted hardware that, again, doesn't achieve the security we want, which is truly untrusted server, and the same for work on non-colluding servers. So really what we want is we want to have all of these properties, okay? One thing I want to mention is that, let me explain why accuracy is so bad with keyword search, okay, compared to semantic search. So not only this trade-off between security and efficiency is hard, but accuracy, whenever, I talked to industry in the past and we only had keyword search, they weren't really, it was more like a toy search. So here's an example. Let's say the user is asking for the meaning of social security numbers. What are those? A keyword search or a lexical search retriever, based on the TF-IDF metric, which is very popular, would return this article. Basically, why? Because a social security number shows up many times. Now, this article has a lot of appearances for social security numbers, but it's not saying what they are. So it's not the right answer. And that's because the keyword search does not understand the meaning of the query. Instead, the semantic retriever understands the meaning of the query. Why? Because these embeddings, right, these great advances in NLP are able to capture the meaning of the query and in embedding space be closer to a document that explains what it is than to one that just has many times occurrences of social security number. Okay, so that's why today's search engines are using semantic search, and that's why we want to support semantic search and not just keyword search. Okay, so basically Compass achieves this. So it achieves both the security and efficiency that we want, And it also has semantic accuracy. In fact, its accuracy is as good as the top performing semantic search on plain text. Top performing semantic search index on plain text. All right, so you might wonder about work on semantic search. Is there any work on search on embeddings? There's a few works. So recently, Tiptoe is a search on public data. So the database is not protected, doesn't match our desired security guarantees. Also, accuracy is low. Then there's a few works that use heavy primitives. For example, Sans combines FHE with garbled circuits and with Oblivious RAM that's distributed, so it's quite slow. And then Srini has a very nice work, Preco, that has good accuracy and efficiency, but it's a distributed server situation. Okay, so we really want to have all of this. We want to have fully untrusted server, semantic accuracy, and we want to be efficient in terms of user perceived latencies. Because it is search on public data, so security here is about protecting the database and queries on it. And so Tiptoe protects the queries, but the database is encrypted. The database is public. Now, if you encrypt the database in Tiptoe, a lot of their techniques no longer work, and it's going to be very slow.
It's a totally different setting.
It's a completely different, it's a different setting. That's why I'm saying this is a different setting. It's private search on public data.
Right.
Security in the sense that you mean, does it?
Yes, in the sense that I mean, absolutely.
They do protect queries, but by definition, they don't protect databases.
Yes, exactly. Yes, exactly.
Exactly. So, and it's not that easy to just encrypt the database because, as I mentioned, their techniques are no longer efficient. Okay, so yeah, there's a bit of work starting to happen in this space, which is very exciting, but there isn't really, what we want of, encrypted search and encrypted database, accuracy and efficiency. Okay, so how do we do this? And really, the way we do it is we set a very ambitious goal. We say, take top performing semantic search index, which is HNSW. It's a top performing semantic search index on plain text. Take that and let's support that efficiently and securely, okay? And let's keep its accuracy going strong. That's what we managed to make happen. And let me tell you a bit more about HNSW, how it works, so that we can then see how we support it efficiently. It's a state-of-the-art index. It's very widely used, and as I said, really performs the best in terms of accuracy. The way it works is that, this name, Hierarchical Navigable, Small Worlds, basically there's a hierarchy of layers, and in each layer you have a proximity graph. Okay? The top layer has a small set of nodes that are farther from each other, and the bottom layer has all the nodes and they're closer to each other. All right. So a search starts from the entry point and does a greedy search in every layer. Okay, finds the local minimum, and once you find the local minimum, you go on the next layer. You find the local minimum there, you go on the next layer, and the local minimum is your answer. All right, it's logarithmic, assuming certain assumptions. I'm not going to go into it, and degree of every node is bounded. All right, so how can we support this? When the database is encrypted. Clearly, the server can no longer do this walk by itself. Everything is encrypted. The server won't be able to tell where to move in this graph. In fact, it shouldn't even know the structure of this graph because that leaks. So instead, the client has to somehow help the server. Okay. So here are some of our ideas at the high level, and then I'll delve into some of them. We're going to depart from using FHE, which is what most of these works use, as I mentioned. And instead, we're going to start with Oblivious RAM. Now, it's going to have some challenges, but we're going to resolve them. Here are the appealing parts of it. First, I'm going to just say at the high level how it works for non-cryptographers here. So basically, Oblivious RAM is a cryptographic technique that hides what you're accessing to storage. So if our user here wants to fetch the second record, it's going to look like with ORAM that they're fetching more records, and it's going to look like random records. And even if you fetch the same record over and over again, it's going to look like you're fetching different random items. Intuition. Okay, so here's what's really nice about ORAM in this setting. Well, it's logarithmic in complexity, that's nice. More than that, it's actually pretty much agnostic of the distance metric and the embedding. What does it mean? Because the client is going to fetch nodes on the client side going to do the distance comparison there, and going to figure out what other nodes to fetch from the server, it can pretty much capture any embedding. We're not stuck to, some FHE optimized embedding or whatnot. And that's nice because that means we can be multimodal easily, have support video search, images search, text search, your favorite embedding. Another thing that's nice, it's actually pretty easy to obtain malicious security, easier than with PIR, right? Because then there's a lot of work that just shows that you can put a Merkle tree on the server side and check it on the client. In this single user setting, it's easy to make sure that there's no tampering that has been done. Okay, now I'll go into that. Now, the challenging part is that it has a large number. So with every node that you fetch in HNSW, you're going to have to do ORAM. So we're going to have a round trip. And there's many nodes that we fetch during a traversal. Could be thousands. Also, it's high bandwidth. You're going to have to fetch all those neighbors. There could be lots of neighbors. Maybe 64 is usually a typical deployment. And they're large vectors. So times 1,000, I mean, that could be high bandwidth. And the fundamental reason why it's so hard, it's so inefficient, like there's the root reason is that these indices, HNSW, were designed for local search on a server. Search on a server, you just move on a server, navigate. They're not designed over the network. When you have a client and a server making queries over the network with ORAM, okay? So that's why at a high level, what we're gonna do to make it efficient is we're gonna have a co-design of the ML technique with cryptographic techniques. So we're gonna change the HNSW algorithm traversal in order to be more friendly to the cryptography and also change the Oblivious RAM to be more friendly to the graph traversal. Okay, so to understand that, let's take an example. So this example is gonna show you why there's a large number of ORAM requests and what we're gonna have to address. So basically, the ORAM client first fetches the entry point, that's the ORAM request, gets a response back. Then it fetches the neighbors, more ORAM requests. Then it fetches the next node, okay, another ORAM request, and so forth and so forth. Lots of ORAM requests, okay? For pretty much every iteration, you do one or more ORAM requests. And this is why this is very slow. On this example, it's seven search steps and 13 visited nodes, but really on a realistic data set, which is something that, user data would be in terms of size, you have more than 1,000 visited nodes, so more than 1,000 ORAMs. And over 36 round trips. So this is too slow for the user. Question?
Listen here, right? I mean, for the multiple layers, it seems inherently sequential.
Yeah.
But search could be somewhat powerful.
Yeah. So for example, this 36. So there's 1,000 ORAM paths to fetch, over 36 steps, and at each step we fetch in parallel multiple ORAMs. This is already including the parallelism. So even including the straightforward parallelism you'll go for, this is slow.
So how do you? So this is compared to without security. What's the X factor?
So this is basically if you use just ORAM off the box and implement this index HNSW on top of ORAM.
But I was like trying to internalize somebody who doesn't care about security.
Yeah.
Being able to know what it would pay.
Yeah. So this is before our techniques. Before our techniques, you would have at least, maybe I would say at least, I probably have 100x slowdown.
No, that's not what's happening. I'm asking what's the insecure version.
Insecure version. Like, what is the payment compared to the insecure version? And not because I don't.
Yeah. So the payment compared to the insecure version for this is at least 100x. Okay, now our payment, just plain HNSW on top of plain ORAM.
So putting plain ORAM is 100x.
Yeah.
It's probably more than 100x, to be honest. I'm being very generous here. Jinhao would just say it's more than 100x.
Why do you want ORAM?
No.
I'm asking what somebody from a company.
I'm saying it should be more insecure.
Yes.
Yeah, and I think also the question is like, if you don't use our system, just do the naive thing. How slow is it? That's basically the question. I would probably say it's more than 100x.
Luca, just kind of in terms of maybe state of the art ORAM, kind of related to Shafi's question. So usually, like in theory, we just describe ORAM like read and write. Here's this algorithm. It seems relatively simple, but it's like, it like computes neighbors and the graph. So in practice, given state of the art ORAMs, how can we kind of make sense if, how slow is it going, right? It's like how to translate this thing to the state of the art ORAM, right? Shafi said it's you said it's 100. Slow down. I'm missing this step because in theory ORAM is just this read writes, but then you translate even something simple to read writes. It looks to me to be millions, and you're saying it's only 100. So how do you kind of assess for state of the art ORAM, given like a plain text, like a normal code, translate it to ORAM? How do we know what is efficient and what is not, or some of the
So just to give you first some intuition, I think there's many questions in that question, but to give you some intuition, so take this is one layer of the HNSW graph, only one layer. The way you put it on ORAM is basically whenever you need a node, you just do an ORAM request, right? So then how much slower is it? Well, it's how slow is it to do a local access to a node on memory or disk versus ORAM? It's more than 100x. It's really probably at least 1,000x. Okay, slower. Now, me being a systems person as well, I know that you need to still pay one round trip to get there. Anyways, I'm not going to get there. So it's less than 1,000 or something. Yeah, so it's slow if you just use it off the shelf. Okay, so here's what we're going to do. So we're going to change. So we're going to have a co-design of the ML and crypto techniques. So for the ML side, we're going to change how we do this traversal of the graph so that it's more friendly to go over the network between client and server with ORAM. And on the other side, we're going to do a wire box modification to ORAM to obtain some improvements for a graph traversal. Then we're going to prove that. All right, so I'm going to tell you at a high level how the techniques work. I might lose some of you in the middle. Feel free to ask questions. Basically, we have two techniques whose goal is the following. We want less round trips between the client and the server. We don't want one round trip per node. And we want less bandwidth. We don't want to fetch all those neighbors times their embeddings and whatnot. So the first technique is the following, we call it directional neighbor filtering. Like the name suggests is we want to embed, compass, a sense of direction into this graph. So this graph in embedding space, two things are close if they're actually close in meaning. So we need to get to some place by walking this graph. So if we have a sense of direction of which direction we need to head, we don't have to fetch all the many neighbors, the 64 plus neighbors. So the question is, okay, for example, let's say that this is a direction, right? This is the query that I need to find, and I'm starting at the entry point. These are this is the right direction, going closer to the query. So maybe we don't have to fetch all the neighbors. Maybe we just have to fetch some part of them. Okay, but the question is, how do we know which ones? Because look, when I fetch this node, I'm going to know the ID of the neighbors, but I don't know their embeddings, because their embeddings are what I'm trying to avoid downloading for all of them. So how do I know which are going to be in the right direction? So the idea is to use a technique. Yeah.
What guarantee do we have on the graph that tells us that going in the right direction is the right thing to do?
So the graph, you can think of it as it still preserves kind of Euclidean distance in an embedding space.
Okay.
Yeah. And I mean, the theory for HNSW, it assumes it's a Delaunay graph, which assumes that basically the greedy search returns like the optimal at every layer. That's how they guarantee log n. But in reality, they're not Delaunay graphs. Again, it's a machine learning technique like any other. They're mostly heuristics, right? They're not fully proven. They're not like cryptographic data structures, right? But if this graph happens to be a Delaunay graph, then it's going to be a logarithmic search and has some nice properties. And we're going to preserve the logarithmic search again under those assumptions. But it's machine learning. It's not really proved fully for the actual graphs in practice. It just happens that in practice, it's very well performing.
So there's some heuristic, there's some greedy search heuristic, and that's the thing you're trying to implement. Is that right? Okay.
So they're doing greedy search at every layer based on moving, closer based on distance metric. But the problem is that with every node, there would be ORAM over the network for us would be too slow. So we're trying to have less round trips, but still preserving the accuracy of this search. Great questions. There's really two worlds here, the cryptographer world and the machine learning world. Very different way of thinking. Great. So how can we get the sense of direction? So the idea is we're going to use a technique from machine learning called product quantization. What's this idea? This idea is we can actually have a compressed version of the data with this, all those vectors reduced in dimension, and have it really much smaller and have it at the client. Obviously, it's gonna not be as accurate, but it still preserves within error the direction in this Euclidean space of embeddings, right? So it's just gonna give us, help us tell which direction we need to go, but in the end, we're still gonna fetch the actual nodes to have a ground truth over what's the actual node we need to go next. So let me explain step by step, because I really threw a lot at you.
You have outlines to graph.
Yes.
To do, but you also have a pre-processed small version of it.
Exactly. This is the main idea of this technique, that we're going to have a compressed version of the graph locally that only gives us a sense of direction, where to head. So we don't have to fetch all the nodes, but only fetch a subset. And the way to compress this is there's a technique called product quantization, really quick intuition for you guys. You take a high dimensional vector, you split it in chunks, and then you look at which centroid it's close to, and the centroids are being pre-trained. Okay, so basically you replace by centroid ID every chunk. Okay, so basically you compress the vector. Okay, so you get a much smaller vector, and these vectors are actually so much smaller, like the compression they can achieve is pretty high. So we can store this on the client side, it's going to be 100 times smaller. Okay, so so now the idea is the following.
So the accuracy here is empirical.
The accuracy is empirical, but if you assume, so we're going to fetch 16 out of 64 neighbors, and assuming again, this Delaunay assumption on an ideal graph and whatnot, then the ideal, the one where we have to go next, the closest will be in one of those 16s, very high probability. And in practice,
is there things that people can prove about this method?
you prove it with assumptions on the graph. So even the HNSW itself is proven under the assumption that it's a Delaunay ideal graph, and the greedy search returns the optimal result. So similarly, under the assumption this product quantization preserves the closest element in the top, the top items that you fetch, then it's going to return the same accuracy.
This might be jumping ahead here, but are you going to be updating this compressed version when the graph gets updated?
That's a very good question. Yes, so we have to update the compressed version when the graph gets updated. So just to give you intuition, so the closest, so you need to go from one vector to the closest vector to the query. That's what you need to do at every step. Now, this compressed set of vectors is not necessarily going to give you the correct closest. But intuitively, if you take the top, let's say 16 out of 64, among those will be the top one. And then what do? For those, you actually fetch their actual full embeddings and compute the actual closest. Okay? So we only use the compressed vectors to filter out some fraction of the nodes, so we don't download all of them, but we still, within those, we look at their actual full-blown embedding and see which one is closer. Okay, so we actually get, within that set, the correct closest one.
So you will save, but just to check it, are you saving here a factor of 100 to 4? Because you said you get only 16 at the end, you get
roughly 4.
Okay, so this is
4.
Good, because otherwise I can
Yeah, and we're gonna get 4, then we're gonna save 16, and we're gonna save another 4, and we're gonna get to under 1 second for search efficiency. Yeah. Okay, so basically just to show you graphically, so we started node 1, and instead of fetching all the neighbors, I'm just gonna fetch 2, because it's just an example. I'm gonna go for 2. Okay, and then this is the closest one. I'm gonna fetch 2 neighbors, doesn't really have to. This third one doesn't have any neighbors. Then I'm gonna go back to this one, fetch 2 closest, and so forth, okay? But what I'm trying to make you see is the fact that the white ones are nodes I never fetched. Okay, so I'm gonna save bandwidth. And how much bandwidth do I save? In this case, I literally, half of the nodes. I basically only had to download half of the nodes, and half I did not have to download. So here I saved half. If you wanna more generally, like you're gonna save this factor of the factor is the parameter of how many we download over m, the number of neighbors. Again, this is gonna affect accuracy for, existing benchmarks, EFN being 16, M is 64, we found that accuracy is basically not affected. Okay, so we're going to save roughly a factor of 4, just to give you some intuitive sense. But in general sense, this is how much we save.
First, you only load 2 and 4 instead of all the neighbors. You will check which one is closer. You will see that 4 is closer. So why do you load 3?
Go back. Yeah, it's a little bit confusing how HNSW works, but here's what happens. So first, my entry point is 1. Okay, then I'm going to fetch the 2 neighbors of 1 that are closest to the query. So these are the 2. I'm going to look at their actual embedding to figure out which is closer. It happens to be this one. Then I'm going to fetch its 2 neighbors, which it doesn't have. So it's just going to be only 1 neighbor that's being fetched. And then I'm going to choose, again, which one is closest, this. Okay. And then this one doesn't have neighbors, so I'm going to go back to this one and so forth.
So you're saying you don't do actually a greedy search, because so you're saying you do exponential search every time by a factor of 2. As opposed, I thought like you do a greedy one. You choose the closest and drop the other one. But
no, so this is basically, we're following the greedy search of the HNSW, the way it works. It's greedy because you can, in principle, have a local minimum. So you can get, in principle, stuck there. In practice, it really is, again, very high performing.
So you're saying in practice, probably few steps. So even though you kind of do exhaustive stuff, I mean, you save a factor of 4, but you still do exhaustive. You don't drop.
Yeah, exactly. Yeah, exactly. Okay. So that was really the intuition, okay? Again, these compressed vectors, we use them only to get a sense of direction, but then we use the actual embeddings as a ground truth for figuring out the next closest step, which allows us to preserve accuracy of HNSW traversal. Yeah, question?
Why do you do greedy search? Because you have a sense of direction, right? So why don't you do directed search in this context? What is the reason for that?
Well, the reason we are doing directed search ourselves, but we're basically just following the HNS greedy traversal, which itself is a greedy search that can get stuck in local minimum. Yes, our modification of it is a directed search, but the original search itself is greedy because it can be local minimum. All right, so now the second technique, okay? So now, great, so we reduce bandwidth, but we still have all these ORAM hops, 1 for every node that we traverse, and could be, many nodes that we traverse. So how can we not do an ORAM request to fetch every node? So for this, we're using a technique that we call speculative greedy search, and it's inspired from computer architecture of speculation, where the idea is that because every fetch is expensive with ORAM, you go over the network, round trip. Round trips are expensive. You can't have too many because the user is going to start waiting too long. How about we just fetch more of those nodes? When we go to the server to get some nodes, let's just get more of them. Let's try to get ones that we think are going to be fetched in the future. So, for example, for this node 1, we're going to fetch this one. This is the next that we need. But how about we also fetch the other neighbor that's second closest? Because maybe we might end up needing it. So the question is, how do we know what nodes we are likely to need? Well, it turns out that if you look at the way the HNSW algorithm works, this greedy search has a candidate list. Okay, and it visits it. Yeah, it visits this candidate list first each node and always picks the closest node in that list to the query. So we have this candidate list. We're only here in this candidate list, but we have all these other entries coming up, likely are going to get fetched in the future, so we're going to fetch them as well. And notice that this technique is not going to affect accuracy at all. Why? Because if we fetch a node that we don't need it, we just fetch too much. If we didn't fetch a node that we need, we go and do an ORAM request. Okay, so this is not going to affect accuracy at all. So let me show you an example, because again, I think it's going to really help clarify. So I have this node 1, and these are the neighbors. Okay. Instead of just downloading this closest node, I'm going to download the 2 closest nodes. Okay, why? Then next, I'm going to download these closest nodes and so forth, okay? So this just saved me from having to do a separate ORAM request for each one of them. And turns out that we actually have a very high hit rate. So as we predict, in this candidate list, we have a very high hit rate. I think it was around 80% in our experiments of actually fetching nodes that are going to end up being used. Okay. Yeah. But of course, everything is from the perspective of the server. We always fetch the same number of items for the same amount of time because we don't want to leak and reveal anything from the number of items that we fetch and for how long. So it's always the same behavior from the server's perspective. Okay, so basically with this technique, we saved roughly, we reduced half search steps. So now if you put both techniques together, they just compose. We managed to reduce the steps of half and the number of nodes we fetched in half. Question, yeah? Yeah.
Function of the embedding that you use.
Yes.
So it could be that different embeddings would impose an implicitly different graph.
Yes, absolutely.
Would be better.
Yes, absolutely. And the nice thing is that
If you use just embedding off the shelf, or you can train an embedding that would be good for you.
both. So the nice thing is our approach works with pretty much any embedding. Why? Because we fetch a node and compute the distance metric of the embedding locally. Locally, you can compute any function you want. So we can actually work with any embedding. In fact, we tested on 4 different embeddings. So you can use whatever is the best on the market, for images or for whatever you want to search.
It could be for your own algorithm and the way you set up this.
That's interesting. Yeah. Yeah, it's interesting if we could somehow train the embeddings knowing the ORAM somehow. That's interesting.
You can sort of rank this on the list of what's the right one.
Yeah, so you always rank them based on the distance to the query, based on a distance metric. So each embeddings come with a distance metric. Could be Euclidean, could be dot product, and is ranked based on the distance to the query. Yeah, but absolutely, yeah. And the way these embeddings actually do get trained based on, like, let's say if it's documents or if it's images, they do get trained. But it's interesting if you can train in conjunction with the ORAM knowledge. That is very interesting. Yeah, we can do that. Okay, so that was that. I'm about to wrap up. These were the 2 techniques. So in the traversal, I'm just really going to quickly mention the ORAM technique because I'm running out of time. So basically what we did with ORAM is that with ORAM, you have this, every time you access an element, you read the stash, and you access a path, and then you evict things from the stash on the path, okay? So you have access, evict, access, evict. Now here's what you can do. You observe that in graph traversal, you have a multi-hop traversal, okay? So, and one thing that you observe is that at every hop, you have actually many, many different neighbors that you're fetching. Okay, so here's very, very quickly. One thing you can do is you can first leverage the literature on batched ORAM to try to fetch all those neighbors at the same time. But more than that, you can actually not evict. You actually don't evict until you're done with the user query. Why? Here's the interesting observation. When you do a multi-hop search, you can ensure on the client side that you don't repeat the same node. Eviction is necessary when you have repeated accesses to ORAM because it's trying to hide that. But if you ensure on the client side that you keep a list of visited nodes and you never request a node again, you can actually just make ORAM accesses with no eviction and do the eviction after you return to the user the result. And that also gives us another 4x really performance in practice. It's really much more than that. So here's an example. You can do access, evict, access, evict, access, evict. Instead, what you can do is you can batch together accesses to neighbors and batch together eviction. So this already reduces number of RAM trips by the size of the batch. But then you can also just do the eviction at the very end and just do ORAM accesses, and that also reduces it. Okay, so this reduces our number of RAM trips by a lot. By this much generally, but in practice, it's really, the batch could be 16, so it could be by 32. And so, of course, whenever you make even the slightest change to ORAM, you have to prove things, right? Because the devil is in the details. So see the paper for formal security proof. And also we had a stash analysis to prove that the stash is not growing too big now that we're just not evicting until very late. All right, so I'm going to just wrap up with some really quick evaluation. We evaluated this on standard search. These are standard search benchmarks that people use in industry for the top performing plain text searches. This is for text-based, this is for images. We can search on images just like for text, just embeddings. And we have 2 baselines. One is if you just use keyword search in ORAM. And the other if you use homomorphic encryption or clustering, which is what some of the schemes are using in the literature. So one thing I want to say is that this is the ideal accuracy that you get if you just scan. So you don't even use the HNSW. People don't do this because they want to use an index to be efficient. Our accuracy is pretty much the accuracy of the plain text HNSW. So we perform as well as top performing plain text index HNSW. And the HE and the clustering has very low accuracy, and the keyword search really has the worst. In fact, on the images, it can't even search because it doesn't know what that is. So the conclusion that you don't have to sacrifice accuracy by using encrypted search. You can really have top performing accuracy, which is what really excites us. And in terms of performance, for example, if you compare to fully homomorphic encryption with the clustering to improve performance, we really are orders of magnitude faster. So this is the performance of Compass, latency, and this is the HE with clustering. And really some really quick takeaways. So if you take a user with 2 terabytes of storage, then a search for this Lion data set is going to be under a second with this. If you take 2 database of storage, that's photos, also under a second. Okay, so the conclusion here is that this is quick search for the user, and you get the usual accuracy that you have with plain text systems today. While also the security is nice because you have fully untrusted server and malicious security. And I remember over time, working on encrypted search, how many times I talked to companies and they always felt that the accuracy is just toy. You guys are giving me a toy search. So now I feel like for the first time, we can actually give an actual proper, high accuracy search for encrypted data through the help of embeddings. And this is also a major component of private RAG. And if you want to read more, that's our paper. And thank you. Any more questions?
Just one. So you start by saying, with plain text search, right? I have stuff in memory, I just go look up, no latency really. And here you pay for latency. So that's just another way one would think of solving this is to use something like TEs. So I don't know when.
Yes. I don't have religion. I'm not religious. But let me put it this way. Let me put this absolutely. You could use TEs as well. And I do also work on TEs, and I do work on pure, just using pure cryptography. Actually, there's a number of in industry. There's a big effort right now towards doing the whole inference process in TEs because NVIDIA has the GPU enclave. But this is the cryptographic approach with no hardware assumption, no concern on side channels from the TEs, no trust the vendor, and you still have good performance. So you could just do this, why not? But I actually see value in both approaches. I'm a fan of both.
The server is untrusted, and you have a TE in the server, and the disk that is storing all of this database is outside, then you still need ORAM.
No, absolutely. But the point is that
no round trips. No round trips. Yeah.
Potentially, so that latency issues are not that pronounced.
Yeah.
Oh yeah.
Absolutely.
ORAM is not,
Completely
it's
agree.
not
Yeah.
over network. Yeah. It's just much
That can make life so much simpler.
So we actually have a paper, Obelix, that does that. So inside the TE, you do a search with obliviousness. In fact, you need double obliviousness. Why? Because the ORAM client lives in the enclave now. So you need to make sure the access patterns that the ORAM client makes are also oblivious. So into the WBS now, you can take Obelix and apply to this. And the advantage, you won't get the round trip so much. But the difference is that this doesn't have assumptions on hardware. You don't need a special. You don't need you don't worry about the side channels, and it's also under a second search. Now, there's trade-offs. I'm a fan of both. I do work on both. I've done both of them.
So my question is about the private RAG. So when you generalize and talk about the RAG,
Yes.
do you have performance like yours to say, or is it?
Yeah. So
the fact that you can use these ideas.
Yeah. So when you get the result back, which is the knowledge, you just send it to a secure inference. So they're like very black box usage of the two, one after the other. So you run us, then you run secure inference, just like that. It's like one after the other. And there's a bunch of secure inference work Some are just using cryptography. It's still pretty slow for like the major transformers today. But there's also work with T's, and
Maybe the keys come up later.
maybe the T's come out later. Yes, also because people tend to have storage and compute in different places. So one place you just don't have any trust assumptions, which is where we have the knowledge database, and then you have the T where you have the model. Yeah. But the nice thing is composes really easily. You do our rag, a retrieval, and then you go into the LLM. In that sense.
So I'm actually curious about your perspective. So one way to think about what you did, you took some particular state-of-the-art algorithm and showed a secure implementation of it. The other, which I'm not sure it's true, would be something kind of more general, saying we built ORAM for a family of graph traversal algorithms, some things which is more accurate. Why do you think you leave? Is it like some new contribution to ORAM, so a very targeted, specific, secure implementation of it?
Very good question. Very good question. You get a good intuition that we have some generality, but not fully, right? So the graph traversal part of ORAM, I would say that technique is quite general to most of these indices because you do graph traversal, and the whole idea is that for the duration of the query, as you go from hop to hop to hop to hop, you don't do any eviction. You just batch, and you can evict at the end. Why? Because you can ensure distinctness. That's general to graph traversal. Now, how about the machine learning techniques? They are focused on HNSW, but they would apply to related graphs where you have this, you also move based on direction and based on closeness. So it apply probably to variants of HNSW. It doesn't apply to LSH, locality sensitive hashing is quite different. So I'd say they would apply to some of the nearest neighbor graph searches, the 2ML techniques. But the ORAM one applies more general to graph traversal.
Within your paper, I guess you focused on a very cool but specific application. It would be nice if,
Yeah, exactly. Yeah, that's a good point. So we can really broaden a bit the scope. Thank you for the feedback. Absolutely, yeah, we can broaden the scope because the contribution is really broader than that. HNSW is the top performing right now, but I agree with you that we want to be more future-proof. Yeah,
Okay, thank you. And we
Thank you.
Nicholas talk at